Here is the most honest thing you can say about a neural network. It is a parameterized function. It takes a vector of numbers, it does some arithmetic, and it returns a vector of numbers. That is the whole structural commitment. Multiply by a matrix of weights, add a bias, pass through a nonlinearity, then multiply and add again. The weights are the parameters, the knobs that training turns. The shape of the computation never changes. Numbers go in and numbers come out. Nothing in that machine knows what the numbers are about.
Wait, when my classifier says 0.9, that number just is the probability, isn't it? The network computed the probability.
That is the natural reading, and it is worth being careful about because it is not quite right. The network produced a number near 0.9. Whether that number is a probability, a distance, a raw score, or an expected count is a separate decision. And the network does not make it. The same output could mean 4 different things in 4 different setups, with not one weight changed. So who decides what the numbers mean? The loss function. The objective you train against is what turns a raw output into a probability, or a prediction, or a rate. The network computes numbers. The loss decides what they mean. Hold on to that because it is the hinge of this whole series. Every architecture and every loss is a bet about the data. Those bets have a name. They are inductive biases, and the right one is what lets a model learn far more from far less. Before the loss, let us look at what the arithmetic alone can and cannot do. Start with the smallest possible network. One linear layer, no hidden units, no nonlinearity. A single linear unit. The function it can represent is exactly a straight line, a flat boundary that splits the plane in two. In higher dimensions, that boundary is a flat sheet, a hyperplane, but the idea is the same. One flat cut, and everything on one side is called one class, everything on the other side the other. It fits anything you can separate with a single straight cut, and nothing else at all. The classic thing it cannot do is called exclusive or. Picture the 4 corners of a unit square. The 2 corners on one diagonal, we label 1. The 2 corners on the other diagonal, we label 0. So the ones sit across from each other, and the zeros sit across from each other on the crossing diagonals. Now try to draw a single straight line that puts both ones on one side and both zeros on the other.
That seems fixable. Surely you just need to find better weights for the line.
It feels that way, but you can prove it is hopeless. Write down the 4 conditions a successful line would have to satisfy, 1 per corner. Add them together, and they contradict each other. The sum has to be positive and negative at the same time. No assignment of weights can satisfy all 4. Train it anyway, and every input drifts to a flat 1/2 and stays there. One straight line simply cannot separate 2 corners that sit on a diagonal. This was Minsky and Papert's argument in 1969, and it stalled the whole field for over a decade. The fix is one hidden layer, with a nonlinearity sitting between the 2 linear maps. And that nonlinearity is not optional, it is the entire point. Without it, the layers collapse. 2 straight-line maps composed together are just one straight-line map, and stacking them buys you nothing. You would have a deeper network that can still only draw a single flat cut. With the nonlinearity in the middle, the hidden units can build intermediate features that are themselves easy to separate, and the output layer simply reads those features off. For exclusive or, one hidden unit can learn the logical or of the 2 inputs. Another learns the logical and of them. An exclusive or is exactly the first of those minus the second. The hidden layer bent the problem into a shape the last line could handle. Here is that network in Scratch, the little pure Python library this series reads from. A network is just a list of layers, plus a loss. A linear map from 2 inputs up to 8 hidden units. A hyperbolic tangent in the middle to bend the space. A linear map from those 8 back down to a single output. And a sigmoid cross-entropy loss bolted on the end. That network learns exclusive or cleanly, where the single unit could not.
So if one hidden layer can fix exclusive, or is one hidden layer all you ever need?
In pure theory, almost. The universal approximation theorem says one hidden layer, made wide enough, can approximate any continuous function on a bounded region to whatever precision you want. But be honest about what that does and does not promise. It says depth is not required. For expressive power, it does not say one layer is efficient. Many functions, a single huge layer could only match at absurd width, are cheap once you stack a few layers. Depth is about economy, not possibility. Now back to the other half, the half the rest of this series leans on. The network body produces raw, unnormalized scores. We call them logits. It never produces a probability. A probability is something the loss computes by taking those logits, squashing them through a link function, a sigmoid, a softmax, or the plain identity, and pairing that with a matching likelihood. The number the network hands you is raw. The meaning is added afterward. And this is where one body becomes many models. Bolt a sigmoid and cross entropy onto the output, and it is a yes or no classifier. Bolt a softmax on instead, and it is a many-way classifier. Use the identity with squared error, and the very same output is now a real-valued prediction. Read it as a log rate with a Poisson likelihood, and it becomes a model of counts. 4 different tasks, 4 different meanings, and not one thing about the network body changed. In the code, forward just runs the layers in order and returns the logits. The loss is what interprets them.
If the body never changes, isn't the loss just a small detail at the end?
It is the opposite of a detail. Here is a fact that looks like a coincidence and is not. For every one of those canonical losses, the gradient with respect to the raw scores is the prediction minus the target. The residual, plain and simple every time. That is not luck. It is what ties the link function to the likelihood, and it is exactly why the next episode asks what noise model a loss secretly assumes. How the gradients actually flow through the layers is its own from-scratch series, coming later. For now, the point stands. Choose the wrong loss, and the same clever network will hand you confident nonsense. Every episode in the series ends the same way, with a scorecard. 3 rows, the same 3 questions for every architecture, and every loss we meet. It is how we keep the whole tour honest, because every bet has an upside and a matching downside. The first row is the bias, the assumption baked in. Here it reads, the outputs mean whatever the loss says they mean. The second row is the win, the payoff when that assumption fits the world. One network body, many tasks, just by swapping the head. The third row is the bill, what you pay when the assumption is wrong. Pick a loss that misreads your data, and the network will stay perfectly confident while being completely wrong.
So the network was never really the hard part.
Not the way we usually think. The arithmetic decides which functions are even reachable. The loss decides what the answers mean. Both are bets, and both are yours to make. Everything from here is this same little network with a sharper bet baked in. Convolution for images, recurrence for sequences, attention for lookup. The math will barely change. Only the assumptions will. The network computes numbers. From here on, we study the bets that decide what they mean.